In this video, we shall prove the following two seemingly challenging identities in trigonometry, 1 and 2. So let's begin. So let us start from the left-hand side of this equation. So the best thing to do this is to expand the brackets. So let's expand the left-hand side term. 1 times 1, so that's 1. 1 times cosecant, so that is cosecant x. 1 times cotangent, so that is cotangent x. Next, secant x times 1, so that is secant x. Secant x times cosecant x, so that's going to be secant x cosecant x. And then secant x times cotangent x, that's going to give you secant x cotangent x. And now the third term of the first bracket, tangent x times 1 is tangent x plus tangent x times cosecant x, that is tangent x cosecant x, plus the third term is tangent x and cotangent x, tangent x cotangent x. So before you proceed, you can see that this term here will be just 1 because tangent x cotangent x is just 1 over tangent x. So that's going to give you 1. So this entire term becomes 1. So let's write that down right away, like that. Now we can try to simplify whatever we have. Let's separate the terms in red and write them out separately. So that's going to be 1 plus cosecant x plus cotangent x plus secant x plus tangent x, and the rest. So the dot terms are the ones in blue. So that's secant x cosecant x, secant x cotangent x, tangent x cosecant x, and that 1 there. So what is this first term here? Secant x cosecant x. So you can simply write it as 1 over cosine x sine x. Now, what about this term here? That term is simply 1 over cosine x. Secant x is 1 over cosine x. Cotangent x is cosine x over sine x. Okay? Which is simply 1 over sine x, or cosecant x. Now, what about this term? So that is tangent x. So tangent x is sine x over cosine x, and cosecant x is 1 over sine x. So you see the sine x cancels each other, and that's going to give you 1 over cosine x. So that means what goes here will be this term plus that term plus 1 plus that term. So I'm going to write whatever appears here at the bottom. Okay, so plus 1 plus, this is 1 over sine x, so that means that will be cosecant x. So this 1 is from here, plus 1 over cosine x, which is just secant x, plus finally this term 1 over cosine x sine x. So for now, let's just write that as cosine x sine x. So we're almost there. Let's look at the last term, 1 over cosine x times sine x. That can be rewritten in the following way. Now, using the identity that cosine squared x plus sine squared x is 1, so we are substituting 1 for cosine squared x plus sine squared x, divided by cosine x sine x. You see that this can be rewritten as quite simply cosine x over sine x plus sine x over cosine x, which is cotangent x plus tangent x. So substituting this result in here, we will get cotangent x plus tangent x. So you see, adding all the terms together, you get 2 plus 2 cosecant x plus 2 cotangent x plus 2 secant x plus 2 tangent x. So they appear 2 times, they just double up, which then becomes 2 times 1 plus cosecant x plus cotangent x plus secant x plus tangent x, which is the result that we want to prove. End of proof. Now let's prove the second identity. To prove the second identity, we need two results. The first result is the fact that sine x plus y equals sine x cosine y plus cosine x sine y. That's the first result we need. The second result we need is cosine x plus y equals cosine x cosine y minus sine x sine y. So we need to use these two identities in here. So let's begin. So let's rewrite sine a plus b plus c as sine a. I am separating a from b plus c. So sine a cosine b plus c plus cosine a sine b plus c. Next, expanding this cosine b plus c and sine b plus c, we'll get sine a, so that is this sine a right there, cosine b cosine c minus sine b sine c. So that is this term. Next, this term. So plus cosine a, I'm going to expand this term now, sine a, sine b, sine b cosine c plus cosine b sine c. Now let's expand these brackets, and that's going to be from the first term here. That's the first term. When you expand the bracket, you get sine a cosine b cosine c minus sine a sine b sine c. Likewise, next this bracket, cosine a sine b cosine c plus cosine a cosine b sine C. So next I'm going to factor out cosine A, cosine B, and cosine C and rewrite this results in here. So I have factored out cosine A, cosine B, cosine C. So to get this term, what do we need to write here? For now, we can just write this as sine A, cosine B, cosine C over cosine A, cosine B, cosine C. So you see, these two cancels, and then it will give you back this term. So I'm just manipulating terms here. We'll do the same to this term. So this becomes minus sine A, sine B, sine C over cosine, so cosine A, cosine B, cosine C right there, and we'll continue with the rest of the terms in a similar way. So now this term here, so that's going to be plus cosine A, sine B, cosine C over cosine A, cosine B, cosine C. And finally this term, which will be cosine A, cosine B, sine C over cosine A, cosine B, cosine C. So the first term in the square bracket, there will be some cancellation. Cosine B cancels, cosine C, leaving you with only sine A over cosine A, so that's tangent A. For the second term, you have no cancellation, so this will give you tangent A times tangent B and tangent C. Now the third term, the cosine C will cancel, the cosine A will cancel, and will give you a tangent B. And the last term, the cosine A cancels, cosine B cancels, and will give you tangent C. So let's write them all together. And we'll get cosine A, cosine B, cosine C, bracket. So the first term in the square bracket is tangent A, this one right here. And then the second term is just tangent A times tangent B times tangent C. The third term is this one, which is tangent B plus tangent B. And the last term will give you tangent C plus tangent C, bracket. So rewriting it a little bit neatly, that's going to give you cosine A, cosine B, cosine C. Let's rearrange the terms. Tangent A, so that's that, plus tangent B plus tangent C plus tangent C, and then minus the product, tangent A, tangent B, tangent C. And this proves the identity that we want to prove. End of proof.